Okay. Uh, so we'll start this discussion session, which is discussion session 5. So in the last session, we talked about extension principle, right? And we saw how it can be used to extend crisp functions to fuzzy functions, right? So I will do a couple of problems on extension principle, and then we'll move to fuzzy equations, which is basically what assignment 6 is about. It's about extension principle and fuzzy equations. So so suppose I start with a function, like a crisp function from x to y, right? So f maps elements of x to elements of y, right? That's what the definition of function is. Now it is it's natural to ask that if we can extend the function f in such a way that f acts on the fuzzy sets of x, and if f is a function from x to y, then f inverse is a function from y to x. So we'd like to extend this f inverse in such a manner that it starts acting on fuzzy subsets of y, right? And we saw that this is what extension principle uh, enables us to do, right? It allows us to extend a function f in such a way that it starts acting on fuzzy sets. And this is how the functions f and f inverse are extended, right? So given a fuzzy set a over x, you apply f to it, and then you end up getting a fuzzy set f of a, which is a fuzzy set over y. And this is how the membership of f of a is given. Similarly, when you start with a fuzzy set b over y, you apply f inverse to it, and you end up getting a fuzzy set over x. And this is how so, so- and this is how the membership function of f inverse of b looks like. All right. And why these extensions are defined in such a manner is what we discussed in the last session, right? We showed that these definitions are meaningful, right? They are a natural extension of f. And we also discussed that ideally we should use different notations for these extensions, right? Because f is a function from x to y. So when we are extending f to fuzzy power set of x to fuzzy power set of y, we should probably use a different notation. So something like this. But for convenience, we don't do that, right? We abuse notation and we retain the original symbols f and f inverse. So let us do a problem. We have two sets, two universe x and y, and we have fuzzy set a over x, and we have fuzzy set b over y, and we have a function from x to y that is given in this manner, and we need to compute f of a and f inverse of b. So by the way, x has a, b, c, and d in it, right? However, this function a does not specify what is the membership of d, right? So I hope you know that that essentially means that the membership function or the membership of d in a is 0. Similarly, here it means that membership of phi in b is 0 and gamma is also 0, right? So for finite universe, we specify fuzzy sets like this, right? We list all the elements and then we specify their membership values. And if any of the elements is not specified, then it automatically means that its membership is 0. So just to clarify. Now let us compute f of a. Now a is a fuzzy set over x. We apply f to it and we get a fuzzy set over y, right? And the membership of this fuzzy set over y is given in this manner, right? So if I need to compute membership of y in f of a, we first of all look at all x that is mapped to y under this function f, and then we simply take the supremum of membership function of a at all those x, right? So suppose I want to compute the membership of mu, right? So this is supremum of ua of x. Now we notice that the set of all x such that f of x is mu is precisely a comma b, right? If you look at the function f, it tells you that a and b are mapped to mu and no other elements are mapped to mu, right? So this means that we are essentially taking supremum over a comma b, which is this, right? And the membership of a in this element a in set A is zero point 0.4, right? And membership of b in A is 0.9. The supremum of these two numbers is 0.9. So this is the membership of U or mu, whatever you want to call it, in the fuzzy set f of A. Similarly, suppose I want to compute the membership of lambda. So we'll look at all x in our domain x such that f of x equals to lambda. Now, it is clear from the definition of f that no such x exists, right? No element in the set x in our domain x in our universe x is mapped to lambda. So this means that we are essentially taking the supremum of the empty set, right? Because the set of all x such that f of x is lambda is simply the empty set, right? No x is mapped to lambda, and this is zero. So I hope you remember that the empty set is has supremum zero, right? This is something we discussed in the last session, so I'm not going to reiterate it again. And similarly, if you want to compute the membership of theta, then we'll first of all look at all x in our domain, which is mapped to theta. So it turns out that c and d are mapped to theta, and no other elements of x are mapped to theta. So that means that we essentially need to take supremum of the membership function of A over C and D. So this we know is 1, and this we know is 0, right? So this whole thing becomes 1, right? Similarly, let us now compute the membership of phi in f of A. So we'll first look at all x in our domain such that f of x equals to phi. Now, no such x exists, right? Because f either maps an element to mu or theta. So this again is the supremum of empty set, and this is 0. So maybe I should not have used this symbol because we already use it for empty set, but don't confuse it with the empty set. It's actually an element. Similarly, membership function of gamma in f of A is the supremum of, so we first of all look at all x that is mapped to gamma, and it turns out that this is empty set again, because f either maps to mu or f either maps to theta. So this again is empty set. So this is 0. So our f of A is 0.9. So this is our fuzzy set f of A. Okay. I hope this is clear. Is there any doubt? Okay. So moving on. So we need to compute the F inverse of B. So B is a fuzzy set over Y. When we when we apply F inverse to it, we end up getting a fuzzy set over X, and the membership of F inverse of B is given in this manner. So to compute the membership of X, you simply compute this quantity. So mu B of F of X. Okay. So let us now compute the membership of A in F inverse of B. So this is nothing but mu B of F of A. Now mu B of F of A is nothing but mu B of U, right? Because F of A is U. And the membership of U in B is 0.2. So this becomes 0.2. Similarly, the membership of B in F inverse of B is mu B at F of B. Now F of B is again U. So this becomes 0.2. Similarly, the membership of C in F inverse of B is mu B F of C. But F of C is theta, and membership of theta in B is zero point 0.7. And similarly, the membership of D in F inverse of B is this. And F inverse of D is again theta, and membership of theta in U is 0.7, right? So our fuzzy set F inverse of B is precisely this set, right? So I hope this made sense to everyone. All we are doing is applying this definition, right? Nothing more. So before moving on, I'd like to make a few comments that would simplify this process of computing the f of A and f inverse of B. So before going into that, I'll just um, discuss a few points about Supremo. So suppose we have a function h from x to unit interval, right? So unit interval is where our membership values come from, right? So that is why we are considering a function h from x to unit interval. Now, if you look at the range of this function, that is h of x, where x comes from domain x, it's going to be some subset of 0, comma 1, right? Because our codomain is 0, comma 1. So the range of h is going to be some subset of 0, comma 1. And this range is going to be bounded because 0, comma 1 is bounded, right? It's bounded above by 1 and bounded below by 0. So therefore, as we saw in the last session, the supremum of h of x over the domain x and infimum of h of x over domain x is going to exist in the unit interval, right? Now, what is interesting is this. Suppose I'm able to write my domain x as union of two subsets p and q. Then taking the supremum over entire x is same as first take the supremum over p, then take supremum over q, and then take the maximum. Now this kind of makes sense, right? So suppose my x is 0, comma 5 and f of x is um, say x by x plus 1. And suppose it looks something like this. Now, if I have to take this supremum of h, so maybe let's call it h of x over x 0, comma 5, then I can first, so since 0, comma 5 is union of 0, comma 2 and 2, comma 5, I can first look at the function h of x over this interval, and its supremum is this point. And then I look at the function h of x in this interval, and then it turns out the supremum is this point, and then you simply take the maximum of these two. And that would give you the supremum over the entire 0, comma 5. right? So basically, the idea is that you can decompose supremum over a larger set X into some smaller subset P and Q, and then simply take the maximum. So I'm not going to prove this, so you prove it yourself, right? So even if you don't want to remember the proof, what you should remember is that you can decompose the supremum in this manner. Now, this is going to help in the following way. So this is basically the definition of how we extend a function f from x to y to fuzzy set of x over fuzzy set of to fuzzy set of y, right? Now suppose I take a fuzzy set over x, then we know that when we apply f to it, I get a fuzzy set over y, and this is how the membership function of f of a is going to look like. Now let us evaluate this membership function at y. Now there are two possibilities. Y either belongs to range of f or y does not belongs to range of f. So we'll look at the first possibility. Second possibility first. So suppose that y does not belongs to range of f. Then that means the set of all x such that f of x equals to y is essentially the empty set, right? That's what it means for y to not belongs to range of f. Therefore, the membership of y in f of a, which is this supremum, essentially becomes the supremum of empty set, which is zero. Which means that you don't have to do all this thing over and over again. If you can simply see that y does not belongs to range of f, then we know for sure that its membership in f of a is going to be zero, right? So this case is, very easy to deal with. The moment you see a y that does not belong to range of f, then you can say for sure that its membership to f of a is going to be zero. Now, let us look at the case when y belongs to range of f. Now, y belongs to range of f means that the set of all x such that f of x is equals to y is non-empty, right? Now, this set can be written as union of two sets. So first of all, so I hope everyone remembers that this is the notation for support of A. And this is basically all those points in X where the membership value is greater than zero, strictly greater than zero. And we also saw in one of the previous session that this is nothing but strict zero cut of A. So anyways, so the set of all X such that f of x equals to y can be written as union of these two sets. So you first of all look at all x in the support of A for which you have f of x equals to y, and then you look at all x in x minus support of A for which f of x equals to y. And if you take the union of these two sets, you essentially end up getting this set of all x for which f of x equals to y. So I'm doing nothing but just decomposing this set into two subsets. So I hope this is fine. I'm first searching for all x such that f of x equals to y in support of A. And then I'm searching for all such x in x minus support of A. And then when you take the union of these two sets, you essentially end up getting set of all x for which f of x equals to y. Now writing this set of all x such that f of x equals to y as union of these two subsets allow us to do this. So when we take this supremum of mu a of x for which over all x such that f of x equals to y, it can be written as maximum of these two supremums. So you first compute the supremum of this set, supremum of mu a of x over this set, then supremum of mu a of x over this set, and then you simply take the maximum. That will give you the supremum over the entire set, this particular set. Okay. Now, for now, let us focus on this set and let us see what is the supremum of mu a of x over this particular set, right? So what we are interested is, so we are interested in this particular supremum. We want to see what this supremum becomes. Okay. Now there are two possibilities. Either this set is empty, or this is non-empty, right? So this set of all x in x minus support of a such that f of x equals to y is either going to be empty or it is going to be non-empty. So suppose if this is empty, then this particular supremum essentially becomes the supremum of empty set, which is zero. Okay. Now what happens when this set is non-empty? Then this particular support becomes support of zero, right? So support of mu a of x, where x comes from x minus support of a such that f of x equals to y. Now we know that there exists such an x, right? So the set over which we are taking supremum is non-empty, right? This is what this means. But if you take any x in x minus support of a, then that means mu a of x is zero, because mu a of x is positive only when x belongs to support of a. So by definition, if you pick any x outside support of a, this becomes zero. So therefore, this means that we are taking supremum of zero over some set. Now that is always going to be equal to zero, which means that this whole supremum is always going to be equal to zero. And therefore, this supremum that we were interested in, supremum of mu a of x over all x such that f of x equals to y, which we decomposed as maximum of these two supremum. Since this is zero, we have maximum of this comma zero, and therefore you essentially are left with this. So therefore, if we were to compute the supremum of mu a of x over all such x such that f of x equals to y, it suffices to just focus on the support of a. So therefore, the membership function of f of a, which is this particular supremum, becomes translates to this nice expression. So if we know that y does not belongs to range of f, then it automatically becomes zero. And if we know that y belongs to range of f, we just need to take the supremum over the support of a such that f of x equals to y. Now, what this means is that we can easily write the membership function of f of a and f inverse of b. So let us consider the previous example again. Now here the range of f is mu comma theta, right? So I hope that is clear to you. The function f from x to y is defined in this manner. So its range is mu or theta. So therefore, if you pick any element of y, set y, except these two numbers, it is going to be equal to zero. The membership function of y in f of a is going to be zero for every y in our set capital Y, such that y is not equals to mu and y is not equals to theta. Right? So you don't need to write all that supremum formula and then compute it. You can simply write that mu f of a of y is zero if y happens to be a member of set capital Y such that does not belongs to range of f. Similarly, suppose I want to compute um, say theta. Okay. Now, by definition, this is this particular supremum, right? And by the way, notice that theta belongs to range of f. So we cannot simply say that this membership function is going to be zero. So we have to compute a supremum. Now we saw that this is same as in this particular case, we don't have to search the entire X. It suffices to just search over the support of A. And what is the support of A? Support of A is basically set of all X such that its membership to fuzzy set A is greater than zero, which in this case happens to be A comma B comma C, right? So I hope that is clear to you. So therefore, we just need to look at A comma B comma C. And in this set, we need to find out for what X f of X equals to Y, f of X equals to theta, and then take the supremum over that particular set. Now, set of all X in support of A such that f of X equals to theta is essentially C, right? So C and D are mapped to theta under F, and only C belongs to the support of A. And therefore this is particular, so this set is singleton C, and therefore this essentially becomes mu of C. Okay, and mu of C is 1, right? And similarly you can compute mu A of U, right? The point is this particular definition of f of A, which the extension principle gives, can be simplified into these two cases, right? When y belongs to range of A and y does not belongs to range of A. And that greatly simplifies the computation. Okay, so let us do one more example on extension principle and then we'll move to fuzzy equations. So we have a trapezoidal fuzzy number and we have a function f from R to R. So it is log of x if x is greater than 0 and it is 0 if x is less than equal to 0. So our function looks something like this. So for x greater than 0, it is log of x. And for x less than equals to 0, it is 0. So it looks something like this. So this is our function f. And we have a trapezoidal fuzzy number a. Now, so a is a fuzzy set over R and f is a function from R to R. So when we apply f to it, we get a fuzzy set f of a over R. And the membership function of this fuzzy set f of a by extension principle is given like this. Again, I'm just using the definition here. So membership function, a membership of y in f of a is the supremum of mu a of x for all x in R such that f of x equals to y, right? Now, let us evaluate this case by case. So let us take a real number y and we want the membership function of y in f of a. This is what we want to compute. Now, so let us look at, so either y is going to be equal to 0 or it is going to be less than 0 or it is going to be greater than 0. There are three possibilities. So let us look at the first case when y is equals to 0. So we'll first look at set of all real number x such that f of x is equals to y, which in this case is 0. So we'll look at this set. So this is the definition of f of x. So if x is less than equals to 0, then f of x is going to be 0. This is what the definition of f says, right? So therefore, any number less than equal to 0 is going to be in this set, right? Because for any x less than equal to 0, f of x is greater than 0. So therefore, this entire real line left to 0, including 0, is going to be in this set. And suppose x is greater than 0, then we know that f of x is equals to log of x. So when is log of x is 0? It is 0 at 1. And 1 is indeed greater than 0, right? So this set of all x such that f of x is equals to 0 becomes this set. So by definition of f, we know that it is 0 for every x less than equal to 0. So this particular set is of course going to be there. And when x is positive, then we know that f of x is log of x. And log of x is 0 at x equals to 1. So we also have to include 1 here, right? So therefore, the membership of 0 in f of a is supremum over this particular set. Okay, now we can break this. Right? So this the set over which we are taking supremum is union of two small sets. So we can break our supremum like this. Now this is basically mu a of 1, right? Because what does this mean? It means supremum of mu a of x where x belongs to singleton 1. So that means it's essentially mu a of 1, right? Now what is mu a of 1? So this is a trapezoidal fuzzy number. And we know that it looks like this. So -2, -1, 1, and 2. So between -1 and 1, the membership function is going to be equal to 1. So I hope that is clear to you, right? So I'm not drawing the graph of the membership function very clearly. But the idea is that if you take any x between -1 and 1, then it is going to belong to A with membership 1. So this becomes equals to 1. So we are taking the maximum of two quantities. One of them is 1, and this number is anyway going to be in the unit interval because it is supremum of membership function, and membership function always stays in the unit interval. So when you take it supremum, you are going to get some number in the unit interval only. And since this quantity is equals to 1, this whole thing is going to be equal to 1. So we don't even need to compute what this quantity is because we are able to figure out this particular thing to be equal to 1. And this thing is anyway going to be less than equal to 1. So the maximum is going to be equal to 1. So the bottom line is the membership function of 0 in f of a is 1, right? So we wanted to compute membership of I equals to 0. That is, we wanted to compute the membership of 0 in f of a. So we started by looking at this set, right? Because we have to take supremum over this set. And we figured out that this set is essentially -infinity to 0 union singleton 1. So we took the supremum over this set, and this supremum can be decomposed into two smaller supremum. And one of those quantity turned out to be equal to 1. Therefore, the entire maximum is equals to 1. And that meant the membership of 0 in f of a is 1. So let us consider the second case when y is less than 0. Now, let us look at this set again. Set of all x such that f of x equals to y. Remember our function f of x is log x if x is greater than 0, and it is 0 if x is less than equals to 0. Now, if x is less than equals to 0, then f of x is equals to 0 by definition. And therefore, our y is always going to be, so the idea is that for no x less than equals to 0, f of x can be equal to y. Because for x less than equals to 0, f of x is equals to 0. However, our y is negative, right? So for any x less than equals to 0, f of x cannot be equals to y. So this case is ruled out. Suppose x is greater than 0. Then in this case, f of x is equals to log of x. So can log of x is can log of x be equal to y? It can, right? So for x e to the power y. So if you take x to the e to the power y, you get y again. And this e to the power y indeed is greater than 0. So this whole thing is nothing but e to the y. To repeat, we want to figure out what this set is. So we first of all looked at less than equal to 0 values of x. And we saw that for such values of x, f of x is equals to 0. Therefore, it can never be equal to y because y is a negative number. Then we started looking at x equals to 0. Then in this case, f of x is log of x. And log of x is equals to y when x is equals to e to the power y, right? And e to the power y, x equals to e to the power y is indeed positive, right? So this whole set is nothing but e to the power y. And therefore, the membership of y in f of a, which is this particular supremum, becomes supremum, which is nothing but this. Now, since y is less than equals to 0, then that means e to the power y is less than e to the power 0 because e to the x is increasing functions, right? So we just need to apply to the both sides. And that means e to the power y is less than equals to 1, right? And e to the power y is anyway going to stay bigger than 0. So when y is less than 0, e to the power y is some number between 0 and 1. For some number between 0 and 1, what is the membership function of that number in A? So A is this particular fuzzy set, right? And we know that for x in -1 to 1, mu A of x is going to be equal to 1, right? That's what trapezoidal fuzzy number is, right? So between -1 and 1, membership function of A is 1. So in other words, this again is 1. Okay. So this case is also taken care of. Now let us come to the case when y is greater than 0. I'll write my function again. So f of x is log x for x greater than 0. It is 0 when x is less than equals to 0. Our This is our fuzzy set A, right? Now let us look at the set f of x such that f of x is equals to y. Again, if x is less than equals to 0, then f of x is equals to 0, and that can never be equal to y because y is positive. So we only are interested in this particular case when x is greater than 0. Then f of x is equals to log of x. So for f of x equals to y, log of x needs to be equals to y, or in other words, x has to be equals to e to the power y, and e to the power y is indeed greater than 0. So in this case also, the set of all x such that f of x equals to y essentially boils down to e to the power y. And we just need to take, so the membership function of y in f of a, right? Now, how do we compute mu a of e to the power y? So y is greater than 0, then that means e to the power y is greater than e to the power 0, that is 1. So from, and what how does the function membership function of a looks like for x greater than 1? So this is basically this portion, right? So between 1 and 2, this is the membership function of a, and after 2 it is 0, right? So this can be divided into two cases. So when one, so, and by the way, what is the equation of this line? It is 2 minus x divided by 2 minus y, which is 2 minus x. So I hope you know how to do all this, right? We are just writing the membership function of a trapezoidal fuzzy set, and I assume that you know how to do that by now. So anyway, so it is 2 minus e to the power y if e to the power y is between 1 and 2, and it is 0 if e to the power y is greater than 2. Basically what I'm saying. So maybe this became a bit. So this is our fuzzy set A, and we know between 1 and 2, the membership function is 2 minus x, and after 2, it is 0. So this is what we are doing here, right? And this is 2 to the power e minus 1. So when does e to the power y is between 1 and 2? When y is greater than 0 and less than equal to ln 2. So I'm just taking the log on natural log on both sides. Similarly, so when y is greater than 0, the membership function of the when y is greater than 0, its membership in f of a is 2 minus e to the power y when y is between 0 and ln 2, and it is 0 when l is greater than when y is greater than ln 2, right? So when y is equals to 0, membership is 1. When y is less than 0, membership of y in f of a is again 1. When y is greater than 0, then its membership is 2 to the power 2 minus e to the power y for y between 0 and ln 2, and it is 0 when y is greater than ln 2. So we computed our set f of a. This is done, right? So the idea is that you just first, given any y, you first of all find this set of all x in the domain that is mapped to y, and then you take the supremum of mu a of x over that particular set. That is all we are doing, right? And we also saw in the last class that most interesting operations are not from some set x to some set y, but they are from set x cross y to z. So our domain is generally made up of two or more sets. So for example, plus is an operation from R cross R to R. Minimum is an operation from R cross R to R. So more often than not, the operations we are interested in have domain that is made up of Cartesian product of two or more sets. So it is natural to ask, how do we apply extension principle in such a setting? More specifically, suppose f is a function from x cross y to z, and I have a fuzzy set A over x and fuzzy set B over y. And we want to compute f of a comma b. The question is, how do we do that, right? So x is a function from x cross y to z. Now, if we knew some fuzzy set m over x cross y, then we can know how to compute f of m. We can simply use an extension principle here, right? So m is a fuzzy set over x cross y. You apply f to it, and you get f of m with a fuzzy set over z. And the membership of this set is given like this, right? So we have a function f from x cross y to z. If you give me a fuzzy set over x cross y, then I can compute f of m by extension principle. So if I have a fuzzy set m over x cross y, I apply f to it and I get f of m, which is a fuzzy set over z. And this is how the membership function of f of m is given. So membership of z in f of m is supremum of mu m, the membership function of m over all xy, such that f of x equals to z. But what we have in this case is a fuzzy set over A and a fuzzy set over B. So from these two fuzzy sets, we need to come up with a fuzzy set over x cross y. If you're able to do that, then we can apply extension principle and then we can compute f of A comma B, right? And we saw in the last session that this can be done from a fuzzy set A over x and a fuzzy set B over y. We can compute a fuzzy set on x cross y by taking the Cartesian product of A and B, which is nothing but the minimum. So again, to repeat, we know how to extend functions of this form, but most interesting functions have domain that is built up of Cartesian product of two or more sets. So something like this. So f is a function from x cross y to z. So domain is x cross y. Now given a fuzzy set A over x and B over y, we want to compute f of a b, f of a comma b. How do we do that? So from fuzzy set A over x and fuzzy set B over y, we first compute A cross B, which is a fuzzy set over x cross y. And the membership function of A cross B is given in this manner. Why this is the case was discussed in the last session, so I'm not going to get into that. The point is, we can obtain A cross B, which is a fuzzy set over x cross y, and then we can apply f of A comma B on. Then we can apply f on this by extension principle. And that would give you this f of A comma B, right? So we first obtain A cross B and then apply the extension principle. So f of A comma B is a fuzzy set over Z, and this is how the membership function looks like. So A cross B is a fuzzy set over X cross Y. We are using the extension principle to write this, but we know that the membership function of A cross B is simply this, right? So basically, this is the formula we get. So I hope this is clear to you. I discussed this in the last session as well. So in case you are having some doubts and want to understand it in depth, I would suggest that you check out the previous session. So let us do a question on this concept. So we have a universe X minus 1, 0, 1, 2, and 3. And we have two fuzzy sets, A and B over X. And we want to identify which of these four options are correct. So notice that minimum is an operation from from R cross R to R. So you give me any two real numbers, I can compute their minimum. So X here, in this case, our universe is nothing but a subset of R, right? So minimum can also be seen as an operation from X cross X to X. Okay. You give me any two numbers in this set X, you give me minus 1 and 1 or 0 or 3 or 1 or 2, I can compute their minimum and that is going to lie in X itself. So minimum can also be seen as an operation from X cross X to X, right? So we have a function F. So here F is our minimum, right? And we are interested in minimum of A comma B. Okay. So how does the minimum of A comma B? So this minimum of A comma B, so A is a fuzzy set over X and B is also a fuzzy set over X. So this minimum of f of A comma B is also going to be a fuzzy set over X. And the membership of this is given in this manner. Right? So so this is basically nothing but set of all x cross y such that f of x comma y is equals to z. F in this case is minimum. So minimum of x comma y equals to z. Okay. So let us compute this expression when z is equals to 0, right? Because that's what the option is about. We need to figure out if the membership of 0 in minimum of a comma b is 0.5, right? So this. So we know we need to look at all x comma y in x cross x such that minimum of x comma y is equals to z, which in this case is 0. And then we are going to take this supremum, right? So let us try to find out set of all x comma y in x cross x such that minimum of x comma y is equals to 0. Now notice that this is our set capital X. So if two numbers from capital X have their minimum 0, then we have following two possible. So one of them has to be 0, right? So we can have 0, 0. If both of them are 0, then minimum of x comma y will be equal to 0. We can also have 0 minus 1. Sorry, 0 and 1, not minus 1. Because if y is minus 1, then minimum of 0 and minus 1 is 1, minus 1. But this case works, right? When x is 0 and y is 1, minimum is again 0. Similarly, when x is 0 and y is 2, again minimum is 0. Similarly, when x is 0 and y is 3, minimum is again 0. And similarly, you just need to take the symmetric cases. So when x is 1 and y is 0, minimum is again 0. When x is 2 and y is 0, minimum is again 0. And when x is 3 and y equals to 0, minimum is again 0. And these are the only x comma y such that a minimum of x comma y is equals to 0. Now let us look at what are the corresponding values of mu a and mu b at these pairs x comma y. So, so okay, so 1 comma 3. So this is basically, as I mentioned earlier, if we have a finite universal set, then we specify fuzzy sets like this. And if any of the elements are not mentioned, so notice that only 1, 2, and 3 are mentioned here, and minus 1 and 0 were missing. So that automatically means that their membership in A is 0, right? Similarly, in this case, the membership of 2 and 3 are not mentioned, then that automatically means that their membership is 0. Anyways, so when x is equals to 0, mu a of x, which is mu of 0, is again 0. So in these four cases, in the first four cases, when x is 0, mu a of x is going to be 0. So regardless of what mu b is, mu b of y, sorry, this needs to be mu b of y. So regardless of what mu b of y is, this minimum is going to be 0 because one of them has become equal to 0, right? Similarly, what is the membership of 0 in B? It is 0.1. And what is the membership function of 1 in A? It is 0.4, 0.9, and 1. So we'll simply take the minimum. And then we'll take the maximum of this column, which is 0.1. This becomes 0.1. Therefore, this option is wrong because it says that the membership of 0 to minimum of A comma B is 0.5, but it turns out that it is 0.1. So again, to summarize, we wanted to compute the membership of zero in this fuzzy set minimum of a comma b. A comma b are fuzzy sets over X, and we want to compute minimum of a comma b. This is how the membership function looks like. So we need to take supremum of this quantity over all pairs x comma y such that minimum of x comma y is equals to 0. So we first find out all such pairs x comma y such that minimum of x comma y is 0. So we had these 7 cases. And in all those 7 cases, we computed this minimum of mu a of x and mu b of y. And then we simply took the maximum, supremum, which in this case is maximum only, right? So this is how you should, evaluate membership values. Again, membership maximum can be seen as an operation from x cross x to x. And therefore, the membership of 2 in maximum of a comma b right? So we first need to identify the pairs x comma y such that maximum of x comma y is equals to 2. So if both of them are 2, then we are fine. Suppose x is 1 and y is 2. So I'm just going to enumerate all the cases. So we have found out all the pairs x comma y such that maximum of x comma y is equals to 2. These are the only such pairs. And then we look at the membership of mu a of x and mu b of y for such pairs x comma y. So when y is equals to 2, mu b of y is 0, right? And therefore, regardless of what mu a of x is, the minimum is going to be equals to 0. Now let us look at the membership function of mu a of x when x is equals to 2. That is 0.9. So this is 0.9, 0.9, 0.9. What is the membership function of 1 in y? It's 0.7. 0 is 0.1. And this is 0.2. So when we take the minimum, we get 0.7, 0.1, and this is 0.2, right? And the maximum of these numbers is 0.7. So this is 0.7. And therefore option B is correct. Now let us evaluate the membership function of U in this. So by this time, this formula should get into your head. We are interested in f of a comma b, where f is plus here. So we will take the supremum of this quantity over all pairs x comma y such that f of x comma y is equals to 0. F is plus here. So we'll look at all pairs x comma y such that x plus y equals to 0. And x and y comes from this set. So what are the possible cases? Either both of them are 0. And one of them is 1, another is -1. So these are the only possible pairs x comma y from x cross x such that x plus y is equals to 0. And you can verify that. If you take any other number, any other pair, it won't have a sum of 0. Anyways, so in this case, this is 0 and this is 0.1, membership of -1 is 0, and 1 is 0.7. And in this case, it is 0.4 and -1 is 0.2, right? So minimum is 0, 0.2. And therefore, when you take the maximum of this, you get 0.2. So this particular quantity is 0.2. And therefore, this option is wrong because it says that the membership of 0 in A plus B is 0.3, right? So I hope this is clear to you. All you need to do is compute this quantity. Therefore, you start by finding out pairs x comma y such that x plus y equals to 0. For each such pair, you compute this minimum of mu a of x comma mu b of y. And after computing all those minimum, you just take the supremum, which in this case is just maximum. So you can use this table kind of approach to solve such problems. And finally, the last option, again, we need to look at all pairs x comma y such that xy is equals to 1. And then we need to take the supremum of this quantity mu a of x and mu b of y over all such pairs. Now, if xy, the pair x comma y comes from x cross x and xy needs to be equals to 1, then we only have two possibilities. Either both of them needs to be equal to 1 or both of them needs to be equal to -1. In this case, this is 0.4 and this is 0.7 and this is 0 and this is 0.2. So minimum is 0.4 and this is 0. So the maximum is 0.4. This is 0.4 and therefore option D is correct. Okay. So when you have an operation where the domain is Cartesian product of two sets, and these two sets can be equal. In this case, for example, x and y were both equal to x. But in general, when you have an operation f, a function f from x cross y to z, and you are given a fuzzy set a over x and fuzzy set b over y, and you want to compute f of a comma b, this is how you go about it. And we have done an example illustrating how to do that. So this concludes the extension principle part. The Okay, so we have one more question. So this is the last question on extension principle. And after that, we'll cover one question on fuzzy equations and conclude the session. So we have two fuzzy numbers A and B. Both of them are triangular numbers. And then we have C and D defined in this manner. And we need to identify which of these four options are correct. Now, again, dot is an operation from R cross R to R. Give me any two real numbers, I'll multiply them and I'll give you another real number. Therefore, if I give you a fuzzy set over R and fuzzy set A and B over R, I should be able to, after applying dot into this, I will get a fuzzy set over R again. I hope I'm clear. So dot is an operation from R cross R to R. You give me any two real numbers, I'll multiply them, I'll give you another real number. And therefore, we want to extend this multiplication operation dot to fuzzy sets over R. So that is, if I give you a fuzzy set A over R and fuzzy set B over R, I want to apply dot into this. I want to multiply them and obtain again a fuzzy set over R. So let's just use the extension principle. We need to take the supremum of this quantity where x comma y comes from R cross R. Notice that our domain x cross y is nothing but R cross R. So therefore, we need to search pairs x comma y in R cross R such that f of x comma y equals to z. And f here is dot. So this is nothing but x cross y equals to z. So this is what extension principle gives us. Now let us see if we can use this formula to identify if options A and B are correct. Now we need to check if membership of 2 in C is 1. So we are interested in pairs x comma y from R cross R such that xy is equals to 2, right? Now, the first pair that comes into our mind is 2 comma 1 or 1 comma 2, right? So these are integer pairs. So these are the first one that comes into our mind. We also have minus 2 comma minus 1, minus 1 comma minus 2, and so on. But these two comes into our mind. Now let us see if that can help us identify if option A is correct. So what if I take, so this is the supremum. So mu A dot B of Z is this quantity. Therefore, it is going to be equal, is going to be greater than equal to for any pair X. So the membership of Z in A dot B is supremum of this quantity, right? So suppose I find a pair X dash comma Y dash such that X dash times Y dash is Z. Then since this is the supremum of all such quantities, it is going to be greater than equal to minimum of mu A of X dash and mu B of Y dash, right? So X dash comma Y dash is one particular pair that satisfy X dot times Y dot X dash times Y dash is equals to Z. And we are taking supremum of all such pairs to obtain the membership function of Z in A dot B. So in particular, this is going to be greater than equal to minimum of mu A of X dash and mu B of Y dash. So this funda will use here. So we know that, so this is one such pair, X dash comma Y dash such that X dash times Y dash is 2. So therefore, we can say, now what is the membership function of 2 in A? Now A is our triangular number minus 2, 1, comma 2. So it looks something like this, minus 2, 1, and 2. But the membership function of 2 in A will be 0. This whole quantity is 0. So by using this particular pair, we arrive at the fact that membership function of 2 in A dot B is greater than equal to 0. So that is anyways known. So this pair is not helpful. Okay. So maybe let us try the second pair and see if it can give us something useful. So x dot comma y dot 1 comma 2, right? And you should be able to see why this pair will be useful because A is this and B is this. So we know that at x equals to 1, membership function of A will be 1, and at x equals to, membership function of B will be equal to 1. And therefore, the minimum of mu A of 1, comma mu B of 2 is going to be minimum of 1, comma 1, and therefore it will be 1, right? So you should be able to identify these things. Now x dot, so this particular pair satisfies the property that x dash times y dash is 1 times 2, which is 2. Therefore, the membership of 2 in A dot B will be greater than equal to. But we just saw that membership function, a membership of 1 in A is 1 and membership of 2 in B is 1. Therefore, this is equals to 1. And membership function in, we know that it is always less than equal to 1 because it is a member of the unit interval. So in other words, membership of 2 in A dot B is 1. So therefore, this option is correct, right? So we saw that we have already discussed in the past that when we need to show if a particular quantity is a particular membership value is equal is 1 is equal to 1, it suffices to show that it is greater than equal to 1. And that is essentially the idea that we have used here. We carefully saw that at x equals to 1, membership of A is 1, and at x equals to 2, membership of B is 2, B is 1, and 1 times 2 is 2. And we need to compute the membership of 2. And therefore, that gave us a hint that maybe this can help. Okay. Now let us, so this we have already done, this is correct. Let us see if this is correct. So membership of, now if we are able to show, this is again, as we discussed earlier, this particular supremum is nothing but this particular supremum, right? That is what we discussed in the starting. That extension, we can simplify the process of computing the membership function using extension principle by simply restricting our supremum from the entire r cross r or x cross y or simply x to the support of the function f. So in this case, our support of a cross support of b. So even if you don't want to use that, it's okay. We'll simply use this formula and let us see if we can get somewhere. Now, if we can find a pair x dash comma y dash such that x dash y dash ka product is 5 and both of them have positive membership value, then their minimum would have a would be positive, and therefore this quantity would be greater than 0, right? So there are two classes of questions that you would often encounter regarding extension principle when you are dealing with product of two fuzzy numbers and division of two fuzzy numbers. First is when is the membership function is equals to 1, which is what option A and option C is about, and when is the membership function is equals to 0, right? So to approach problems of first type, when you need to figure out if the membership function of a particular, if the membership value of a particular number is equals to 1 in C or D, you need to find out a pair x dash comma y dash such that x dash times y dash is equals to that number. In this case, it was 2, such that both of them belong to their fuzzy set with membership 1. And if you're able to do that, then the minimum of those two membership value will be equal to 1, and you'll be able to show that the membership of number 2 in C would be equal to 1. Similarly, if you want to check if membership of 5 in C is 0, it suffices to figure out if there exists a pair x dash comma y dash in R cross R so that x dash times y dash is equals to 5. And these and their membership to their corresponding fuzzy sets is greater than 0. Because if you are able to do that, then you'll be able to show that the membership value of 5 in C would be strictly greater than 0, right? So this is a standard approach. So you should be able to you should be able to think like this, right? You want to see if this is true. And this is not true if you're able to find such a pair x dash comma y dash such that these things hold, right? So the first thing that should come into your mind is, can we find such a pair? If we can find such a pair, then of course this option is wrong. But if not, then maybe we'll have to do something extra to show that the membership of 5 in C is 0. Now the question is, how do you find it, how to sort of perform this kind of search? How do we search R cross R such that x dash times y dash is equals to 5 and the membership function of A and B is greater than 0? So when is the membership function of B is greater than 0? Let us start by looking at this. And when is the membership function of A is greater than 0, right? So therefore, what we are interested in is this particular. So this is our entire plane R cross R, but we don't need to search this entire plane R cross R. It suffices to perform our search in this particular square, right? Because it's only when x is between -2 and 2 and y is between 1 and 3 that both mu a of x and mu b of y is greater than 0. And we want both of them to be true, right? In order to find out such a pair x dash comma y dash. Therefore, we don't need to search the entire R cross R. It suffices to search this. So I hope that is clear. Now, suppose that we have found a pair. So let us suppose that there exists a pair x dash x dash and y dash such that x dash times y dash is 5. Then that means that x dash is 5 by y dash, right? Now, so I'm running out of space here, so maybe I'll erase some. Right now, we want y dash to be between 1 and 3, and therefore 1 by y dash would be between 1 by 3 and 1, and therefore 5 by y dash bet- would be between 5 by 3 and 5, right? And this is nothing but x dash. And at the same time, we want to ensure that x dash needs to be between -2 and 2 because we want mu a of x dash to be greater than 0. And we found out a range for x dash here as well. So it makes sense to simply take 5 by 3 and 2 ka middle point. Okay, so I'll just repeat. We want a pair x dash comma y dash with these properties. Then I argued that you don't need to look at the entire R cross R. You just need to look at this particular square. -2 comma 2 cross 1 comma 3. Because it is precisely in this interval, in this region of R cross R, that both membership function of A and membership function of B is greater than 0. Then we suppose that मान लो कि we are able to find x dash and y dash such that x dash times y dash is equals to 5. Then x dash will become 5 by y dash. Now we know that y dash needs to be between 1 and 3. Therefore, 5 by y dash needs to be between 5 by 3 and 5. And we at the same time, we want to make sure that this x dash comes from -2 comma 2. So what we'll do is that we'll simply take 5 by 3. We'll simply take x dash to be 5 by 3 and 2 ka mean. So we'll ensure that x is somewhere here at the middle. Now this quantity is 11 by 6. And when x is 11 by 6, x dash is 11 by 6, y dash, which is 5 by x dash, would become 30 by 11. So long story short, we're able to find x dash in -2 comma 2 and 1 comma 3 and y dash in 1 comma 3 such that x dash and y dash is 5 and mu a of x dash is greater than 0 because it belongs to -2 comma 2 and mu b of y dash is greater than 0 because it belongs to 1 comma 3. So in other words, we are able to find such a pair x comma y dash with these properties, and therefore the supremum would be greater than equal to minimum of mu a x dash comma mu b y dash. Now, since both these two quantities are positive, this has to be positive, and therefore this can definitely not be the case. So I hope that is clear to you. So there are two classes of questions. In first class, you are required to check if membership of some number, in this case 2, to C is 1. In that case, you should find a pair x dash comma y dash such that x dash times y dash is equals to 2, and both the membership value is 1. And in the second class of question, you want to check if the membership function of 5 in C is 0. Now, your first instant should be to check if we can contradict this. If we can find a pair x dash comma y dash such that x dash belongs to A with positive membership, y dash belongs to B with positive membership, and x dash and y dash ka product is equals to 5. If you're able to do that, then you can contradict that the membership value of y of 5 in C is 0. I hope I gave you some sense key how to approach questions like this. So in option C, we need to check if membership of half in D is 1. Now, again, it should strike that membership of 1 in A is 1, membership of 2 in B is 1, and 1 by 2 is what we have here. So membership of half in D, which is this particular supremum, is greater than equal to, right? Because x dash comma y dash equals to 1 comma 2 is a pair in R cross R such that x dash comma y dash is 1 x dash divided by y dash is 1 by 2. We are taking supremum over all such pairs, so that supremum will definitely be greater than equal to mu a of x dash, which is mu a of 1, comma mu b of y dash, which is mu b of 2. This is minimum of 1 comma 1, and this again is 1. But membership function is always in the unit interval. And if it is greater than equal to 1, then that means mu d of half is 1. So this option is correct. Now, let us look at this. So now you can adopt the previous approach that we discussed. If we can find x in support of A and y in support of B such that x by y is equals to 0 and both their membership function is greater than 0. In that case, we'll be able to contradict. But that approach is useful only when we have an option of this form, right? It's only when you are able to, only when you're dealing with options like this, that that particular approach will work. Because in that particular approach, we're just able to show that the membership function of 0 in D or 2 in D or 5 in D, whatever number you have, is greater than 0. However, in this case, we need to check if it is a particular, we need to check if it is equal to a particular value. So in such a case, you need to look at the supremum and try to simplify it. So notice that if x comma y is a pair in R cross R such that xy equals to 0, then this is same as saying that x is any non-zero real number. Which means x is any real number and y is any non-zero real number. First of all, observe this. We are saying that for two real numbers x by y is equals to 0. Now, this can only be the case when y is non-zero. First of all, this x by y needs to be meaningful. And we know that 1 by 0 is not defined, right? So y definitely has to be non-zero and x needs to be 0. Sorry. So when x is 0 and y is any non-zero number, then x by y is equals to 0, right? So up any pair x comma y such that x by y equals to 0 essentially is if and only if with x is equals to 0 and y is non-zero, which means this supremum is essentially this particular supremum. So so here x is constant, x has to be equals to 0. So we'll simply put x 0 there, right? Now let us draw the graph. So we need to evaluate mu a of 0. Now I hope you know how to do that, right? A is a triangular fuzzy number and we need to evaluate its membership as 0. So this is basically x by 2 plus 1 by 2 at x equals to 0. So this is uh, 2 by 3, right? And verifying. Okay, so this is 2 by 3, right? So minus 2, 1, and 2. So this equation is x plus 2 divided by 3. And at x equals to 0, you have 2 by 3. So this becomes supremum of 2 by 3. Okay. Now it automatically makes sense to find all y such that because in for such y, minimum of 2 by 3 comma mu b of y will become 2 by 3, right? So in other words, it makes sense to compute 2 by 3 cut of b, right? Now let us do that. So 1, 2, and 3. So this is our triangular fuzzy number b. This is x minus 1 and this is 3 minus x. Therefore, alpha cut of a for alpha greater than 0 would be alpha plus 1, 3 minus alpha. Therefore, so sorry, this is beta. So 2 by 3 cut of beta. So I'm just glossing this step over because I hope you know how to do that. So I just found out the alpha cut of b, and then to compute 2 by third cut of b, I'll simply put 2 by 3 here. This is 5 by 3, 9, 7 by 3, right? So for all non-zero y with y in this interval, mu b of y is greater than equal to 2 by 3, and therefore this minimum of 2 by 3 and mu b of y is again 2 by 3. Okay. Now, this is the supremum we need to find. Now, this can be broken into two supremums. That is why in the start I talked about how you can break supremum because it comes very handy in many questions. So I'm breaking this supremum into two parts. Right? So we need to take supremum over all non-zero real numbers. So we can first take supremum over all non-zero numbers so that y is between 5 by 3 and 7 by 3. And then we can take its supremum over all non-zero numbers so that y is less than 5 by 3 and y is greater than 7 by 3. So this we found out is nothing but 2 by 3. And therefore, when you take the supremum, you essentially have 2 by 3. So you're left with this particular supremum. Right? So this is mu b of y. This is 2 by 3. And this turned out to be 5 by 3. And this turned out to be 7 by 3. Right? And we want to just evaluate this particular supremum. Supremum of minimum of 2/3 comma mu b of y such that y is non-zero real number and y is less than 5 by 3 and greater than 7 by 3. Okay. So for y less than 5 by 3, we are essentially looking at this particular part of the real line. And for y greater than s by 3, we are looking at this particular part of the real line. And in this particular real line, so when y right, because till 5 by 3 the membership value increases to 2 by 3. So when you approach 5 by 3 from left hand side, the membership value keep on increasing, but it goes all the way to 2/3. Similarly, when you approach 7 by 3 from right hand side, the membership value keep on increasing and it goes all the way to 2 by 3. But since 5 by 3 and 7 by 3 are excluded, that membership value 2/3 is never really achieved. So when y is non-zero number says that y is less than 5 by 3 and y is greater than 7 by 3, mu b of y is in this particular interval. So when you take the supremum over this particular set of mu b of y, you end up getting 2 by 3. Therefore, this membership value of 0 in D, which was this particular quantity, is nothing but 2 by 3, and the second supremum also came out to be 2 by 3. So this is again 2 by 3. So this is 2 by 3. And therefore, this option is wrong because it says that the membership of 0 in D is 1 by 3. To summarize, we were interested in finding the membership value of 0 in D. D is A by B. So we use the extension principle to write this. And then we observed that if x comma y is a pair of real numbers such that x by y is 0, then that is same as saying that x is 0 and y is some non-zero real number. So therefore, this supremum can be broken down into this supremum, right? Now, x is 0 here, so we can simply put 0. And we turned out that the membership of 0 in A is 2/3. Therefore, we need to take the supremum of minimum of 2/3 with membership function of B such that y is some non-zero real number. And that supremum can be broken into two parts, as we discussed earlier, that any supremum can be broken into two parts. The first part is equal to 2/3, and the second part is also equal to 2/3. Therefore, you have mu d of 0 as maximum of 2/3 comma 2/3, so it's 2/3. Therefore, this option is wrong. So these were the few problems on extension principle. It will help you solve almost all the problems that there are in assignment 5, assignment 6, based on extension principle. Now I wanted to discuss fuzzy equations as well, but it seems that we are running out of time. So maybe I'll just do one problem and get done with this session. Okay. So I won't go into a lot of details. I wanted to discuss how actually this whole apparatus of solving fuzzy equations came into picture. But in interest of time, I'll simply solve a particular problem. right? So I'll just give a bit of background and then I'll move to the question, straight to the question. So we all know how to solve linear equations involving real numbers, right? So 2x plus 3 equals to 5. Then we know that x equals to 1. We know how to solve such equations. So it is natural to ask that if we can solve equation involving fuzzy numbers, right? So more specifically, we want to solve equations of the form ax plus b, a plus x equals to b, a dot x equals to b, where a and b are fuzzy numbers. And we want to find a fuzzy number x, right? So we want to solve these equations in the space of fuzzy numbers. Okay. Now I'll deal with this additive fuzzy equation a plus x equals to b. So we know fuzzy numbers a and b, and the goal is to find a fuzzy number x such that a plus x equals to b. Now suppose that such a fuzzy number exists, then what are the things that we can say about this fuzzy number x? Firstly, since a, x, and b are fuzzy numbers, then for any alpha greater than 0, its alpha cut can be written as closed intervals, closed and bounded intervals, right? That's what the definition of fuzzy number is, that any alpha cut for alpha greater than 0 is a closed and bounded interval. So therefore, for any alpha, suppose the alpha cut of A looks like this. So it's alpha A1, comma alpha A2, and alpha cut of X is X1, comma X1 of alpha, comma X2 of alpha, and alpha cut of B is alpha B1, comma alpha B2, right? So the reason why I'm not using X1 of alpha is because X is something that we need to figure out, right? While on the other hand, A and B are known. So alpha A1, alpha A2, alpha B1, alpha B2 can always be found. But X is something that we don't know. We have assumed that it exists, but X1 and X2 are yet to be figured out. So that's why I'm using X1 of alpha. Anyways, now since we know that this fuzzy number X satisfies this equation, then that means the alpha cut of A plus X would be equal to alpha cut of B. But alpha cut of A plus X is same as alpha cut of A plus alpha cut of X. So this is equals to alpha cut of B. So in other words, when you add alpha cut of A with alpha cut of X, you get an alpha cut of B, which means that when you add these two closed and bounded intervals, you get this, which is same as saying that this is equals to this. So these two closed and bounded intervals are equal, which means their corresponding endpoints are equal. Therefore, alpha A1 plus X1 of alpha is equals to alpha B1, and similarly for 2. Therefore, you can figure out X1 of alpha and X2 of alpha, right? Now, we know that X is a fuzzy number, and any alpha cut of a fuzzy number is non-empty. And I hope that is clear to you because X is a fuzzy number, which means it is normal. Therefore, there exists X naught such that mu X of X naught is 1. And 1 is greater than equal to alpha for any alpha greater than 0. Thus, X naught will belong to alpha cut of X for any X for any alpha greater than 0. In other words, any alpha cut for alpha greater than 0 is non-empty for a fuzzy number X. So therefore, this alpha X needs to be non-empty for every alpha greater than 0. Now, when will this be non-empty? When the left endpoint is less than equal to right endpoint. For example, if I write something like minus 1 comma, so maybe I should write. What is this interval? This interval is nothing but the empty set because this interval consists of all numbers x, all real numbers x that is greater than 1 and less than equals to 0. But no such number exists. Therefore, it is empty set. So therefore, for this alpha x to be non-empty, the left endpoint needs to be less than equal to the right endpoint, which means that this condition should hold. Okay. Furthermore, any fuzzy number is nothing but a fuzzy set, and fuzzy set ka alpha cuts are nested. That much we know. That is when alpha 1 and alpha 2 are numbers in the unit interval, so that alpha 1 is less than equal to alpha 2. Then that means the alpha 2 cut of x is contained in alpha 1 cut of x. Now, this condition is equivalent to this condition. I hope you are able to see why. right? Because when this holds, it essentially means that alpha 2 of B1 minus alpha 2 of A1, comma alpha 2 of B2 minus alpha 2 of A2, this closed and bounded interval will be included in, but this is precisely alpha 2 cut of x, and this is precisely alpha 1 cut of x, right? So this condition that the alpha cuts of x should be nested translates to this. So in books, you'll find this condition, but all this means is that the alpha cuts of x are nested. Now, therefore, to summarize, we assume that a fuzzy number x exists such that ax plus x equals to b, right? And then we found out that this is how the alpha cuts of x looks like, and these two conditions hold. Now, what is interesting is that the converse also holds. What do I mean by that? It means that if I consider a fuzzy set x with this particular alpha cuts obtained by subtracting the alpha cuts of b and a, such that for every alpha greater than 0, alpha x is non-empty, and for every alpha 1 and alpha 2 with alpha 1 less than alpha 2, this holds. And furthermore, all these alpha cuts are bounded. So basically, this condition means that if you pick any alpha cut, alpha 1, it is contained in m comma m, which means that basically all alpha cuts are bounded. So if you can find such a fuzzy set x, then x is a fuzzy number and it is the unique solution of ax plus b. And this is basically what we use to find out the solution of these fuzzy equations of this type. So to summarize, from a and b, we can find these quantities. From that, we can construct this closed and bounded interval. If this closed and bounded interval alpha x satisfy these two properties, that is, they are non-empty, they are nested, and furthermore, all of them are bounded. The next is a fuzzy number, and that is easier to see, right? Because uh, this condition implies that 1x is non-empty, therefore x is normal. This this means that x is a closed interval for all alpha greater than 0. And this means that alpha cut of x is bounded for all alpha greater than 0. And this essentially means that the support of x is bounded. So these three properties taken together automatically implies that x is a fuzzy number. And moreover, it is a unique solution of ax plus b. Right. So this is basically the funda we use to solve ax plus b, equations of the form ax plus b. Right. So all this may seem bit complicated, but we'll do an example and you'll find that it's very easy. Nothing very, very fancy. So we have two fuzzy numbers a and b over with the real line, and we need to find out a fuzzy number x such that ax plus b, such that a plus x is equals to b. Now, um, let us first of all let us write the alpha cuts. Okay, so I'm not going to explain what I'm doing here. I hope that is clear to you. I'm just finding the alpha cuts. right? So A and B are these two fuzzy sets, and the alpha cut of A and alpha cut of B for alpha greater than 0 looks like this. Now let us consider X alpha, which is this minus this minus this. So what is this? So we define fuzzy set X with these alpha cuts. Now we need to verify certain properties. First of all, this should be non-empty. That is, the left endpoint must be less than equal to the right endpoint. But this is the case only when 3 is less than equal to 2 alpha. And that in turn is the case only when alpha is greater than equal to 1.5. But alpha is in this interval. So it can never be greater than equal to 1.5. And therefore, alpha minus 3 is never less than equal to alpha. Minus alpha plus 3 is never less than equal to alpha. And therefore, this alpha cut of X is always empty. Therefore, no fuzzy number X exists such that A plus X equals to B. To summarize, we had fuzzy numbers A and B. From that, there we computed the alpha cut of A and alpha cut of B. And then we supposed that X is some fuzzy number that satisfies AX plus B. A plus X equals to B. If that is the case, then the alpha cut of X would look like this. So you subtract the left endpoint of B with left endpoint of A, alpha A, and similarly right endpoint of alpha B with the right endpoint of alpha A. So this is basically the alpha cut of X. Now this alpha cut of, since X is a fuzzy number, this alpha cut must be non-empty for every alpha greater than 0. But it turns out that is not the case because the left endpoint is always strictly greater than the is strictly greater than the right endpoint. So therefore, no fuzzy number X exists such that Ax plus B equals to A plus X equals to beta B. So in other words, no such no such X exists. Now let us look at another equation, other question. Ax plus b. Again, we have two fuzzy numbers a and b, and we need to find a fuzzy number x such that a plus x is equals to b. Now you can be a bit clever here. We know how to add two triangular numbers very easily. So if a1 is alpha 1, alpha 2, alpha 3, and a2 is beta 1, beta 2, beta 3, then we know that a1 plus a2 is nothing but this triangular number that is obtained by adding the corresponding parameters. Now, if you take x to be 4, so 2 plus 4 would be 6. If you take the second parameter to be 6, so 4 plus 6 is 10. And if you take last parameter to be 8, then 7 plus 8 is 50. Then a plus x would be 16 and 15, and that is precisely b. And therefore, you know that x, that is triangular number 468, is a solution. And in fact, it is a unique solution because if a solution a plus x equals to b exists, then it is the unique solution. So you don't need to do all the arithmetic. It turns out that you can very easily figure out a solution of this equation. You could have tried doing the same thing in this particular question as well. We know that when we have two trapezoidal numbers, and by the way, this is something that I discussed in a previous session, that if you have two trapezoidal numbers and you want to add them, then it is same as adding their corresponding parameters. So we want to add something to -2 to get 1. So we need to add what? 3, right? Similarly, we want to add something to 0 to get 2. So 2. We want to add something to 2 to get 3, 1. And we want to add something to 4 to get 4, 0. But is it a meaningful trapezoidal number? No, right? Because a trapezoidal number must satisfy these conditions. So the leftmost parameter needs to be less than equal to the second leftmost parameter and so on. In this case, we have 3 to 1, 0. So this approach that we employed to solve this second problem, right, and which essentially helped us bypass all the arithmetic. We simply, intelligently guessed a fuzzy number x such that a plus x equals to beta. This kind of cleverness won't work here because that ends up giving you a trapezoidal fuzzy number x that simply is not meaningful. So here you had to sort of do all this arithmetic to prove that, to find out if such a fuzzy number x actually exists or not. But the first thing that you should come to your mind when you are dealing with fuzzy equations where you have fuzzy numbers a and b is to do something like this. When a and b both are triangular fuzzy numbers, so you should think that, okay, can we construct a triangular fuzzy number x such that a plus x equals to b, right? So that's a clever way of solving fuzzy equations. And this is in fact a unique solution because this in fact is a unique solution because if you assume that x dash is some other solution to this equation, then you can show that x is equals to x dash. And that is not difficult because since x dash satisfies this equation, then that would mean its alpha cut will look like this. So it's alpha b1 minus alpha a1, comma alpha b2 minus alpha a2. And since x satisfies this equation as well, so alpha cut of x would also be this same. So what you are able to then show that alpha cut of x dash and alpha cut of x is same for all alpha greater than 0. And that means that x dash is equals to x. So maybe I should have discussed this in the beginning. I had slides for that, but I did not use it. So whenever we have two fuzzy sets A and B over X, we call them equal, denoted by A equals to B, when their membership function coincides for every member of the universe. And you can show that two fuzzy sets A and B are equal if and only if all their alpha cuts for alpha greater than 0 are same. Now, prove this yourself. It's not very difficult to prove. But what you should remember is that to show that two sets are equal, two fuzzy sets are equal, it suffices to show that all their alpha cuts for alpha greater than 0 is equals to, uh, for alpha greater than 0 is same. So the point being that we cleverly guessed a fuzzy number x such that a plus x is equals to beta. And that fuzzy number x is necessarily unique. So there are no any other solution. So there are no other solutions. And that can be easily shown in this manner. Let you simply compute the alpha cut of x. This would look like this. And suppose that x dash is some other solution. So the alpha cut of x dash will also look like this. And therefore x dash would be equal to x. So anyways, so x is 468. Therefore, the membership value of 6 in x will be equal to 1. That's what triangular fuzzy numbers behave. So A is definitely normal, right? Now we are interested in finding the height of this. So let us first of all figure out the intersection of A and X, where this intersection is the standard intersection, because that's what this subscript M indicate, right? So it's the intersection with respect to minimum T norm. So you have 2, 4, 6, 7, and 8. So A is 247. this is A, and X is 468. So their intersection would look something like this. And height of is nothing but that's the definition of height, right? It is the supremum of the membership function. So basically, it is very clear that since this is the graph of the membership function of A intersection X, so this is the height, right? So this point P corresponds to the height. The y coordinate of point P is the height. And we can easily figure out. So what is the equation of this line? It is x minus 4 by 2. And what is the equation of this line? It is 7 minus uh, just a minute. So this is 8 minus x by 4, right? And basically, point P is precisely where these two lines intersect. So we'll just need to solve this equation. So 2x minus 8, 8 minus x. So x is 16 by 3. Am I right? This is A is 247, 247. And then we have x, which is 468, right? So 468. So this is x minus 4 by 6 by 4. So this is x minus 2. And this is 7 minus x divided by 7 minus 4. This is 3. My bad. Okay, so maybe I'll skip doing this. The point is that now you can easily solve this problem, right? The tricky part was this. Okay, how do you find an x? Once you have an x, then these options are very easy to figure out. No such x is definitely incorrect because we have already found such an x. And then you just need to find a intersection x, and you need to find the height, and you need to find the membership of A. Now, all that is very easy, right? We have already done this again and again in different assignments. So the point is that, you know, you can, whenever you are dealing with equations of this form and you know that A and B are triangular or trapezoidal fuzzy numbers, you can try to make an educated guess for X. So I wanted to discuss one example of this type of fuzzy equations as well, but it turns out that we are running out of time. So maybe I'll just share these slides and you can go through it. They are sufficiently detailed, so I hope it should not be an issue. You just need to fill in these gaps, and that is easy to do because I've already like indicated in detail how to actually derive the method to solve such equations, right? So I hope you found this session useful, and that is it. So anyone has any questions?
Sir, is the recording of the first and the second discussion session also available somewhere?
Unfortunately, no. So I used to conduct initially the sessions used to be conducted on Google Meet, and somehow Google Meet does not have a recording option, at least the NPTEL ID that I use. So unfortunately, no. I do have the slides on the drive though. So I have uploaded the slides and you can find them. And I've also sort of edited those slides. So instead of having all these like cumbersome uh, 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 details. I made them like really nice. I edited them, and you can easily you should be able to understand those slides easily. So even if you don't have the recording, you should be able to understand the slides.
Okay, sir. Okay, thank you, sir. Thank you, sir.
Anything else? Mani, Jaya. Is there any
No,
doubt,
sir,
Jaya? Or
not right now, not right now. But I was
okay,
having doubt in first, second assignments for like preparing for exam, but I heard right now that the recordings are not available. So I hope you will help me if and there are some doubts in first three assignments or questions related to that.
yeah, definitely. I
Yeah,
have already uploaded the solutions as well, and the
yeah,
slides are also there. So you
yeah,
go through them, and if you think that
yeah,
you're not able to understand something, you can email me or put it into the
yeah,
discussion forum so that I can reply or others can reply.
yeah. Sure, sir. Thank you so much.
Okay. And Mani, anything?
No,
Do
sir.
you have any question? Okay. In that case, thank you for joining. And so I think after this assignment, after assignment six, you will week seven is about fuzzy relations, and fuzzy relations are sort of fairly easy, at least the starting part. In fact, in general, so the hard part is now over. So fuzzy arithmetic is generally the considered as the hard part of this course because you have to do a lot of calculations. It's calculation heavy. Although I tried giving motivation for all the methods that we use in fuzzy arithmetic, right? So the good news is that hard part of the course is now over, and now you have fuzzy relations, and then you'll have a bit of approximate reasoning, and those are fairly easy to follow. Not a lot of calculations. So now the course would uh, would sail very smoothly. Okay, so again, thank you everyone for joining, and I'll end the meeting now.